Thanks for the introduction. So, in the thematic of this morning, I'll be talking about the strong convergence for operator with, for polynomial of random matrices with operator-valued coefficients. So before I actually go into any form of actual detail, I would like to state some very basic definition. I assume most of you are familiar with the notion of tensor, but that's not always the case in the random matrix theory. So just to be clear, if we take two matrices A and X, one of size M, the other one of size N, then A tensor X is the following matrix of size, well, N in some sense, but of size M, but where every entry is this time itself a matrix of size N. So the resulting matrix is a matrix of size Nm by Nm, basically. All right. So now, once you've defined that, I can define a notion of a polynomial with operator-valued coefficient, or rather matrix-valued coefficient. And to do so, well, that's pretty simple. If you have a regular polynomial, well, it's just a linear combination of monomials. Well, here that's the same thing. That's a linear combination of monomials, except that our coefficients here are not scalar anymore. They are themselves matrices. And of course, to give some sense to this multiplication, well, you need to take the tensor, because AL is not the same size as this matrix L of Xn. All right, so that's our polynomial, our matrix-valued polynomials. And so the big question that came with the work of Ben Hayes was, how do we control the norm of that thing? And well, if you want the signature coefficient to be fixed, then it's very straightforward. That's just an immediate consequence from the result of Hagoop and Peterson-Thom. But the point of Ben Hayes' conjecture was that you absolutely needed those coefficients AL to have their dimensions to depend on large N, the dimension of your random matrices. And more precisely, you needed them to have the exact same dimension. So that brings us to the following problem, how do we control the norm of this thing, of this operator, when the size of the coefficient is fluctuating with the dimension of your random matrices? So, all right, so let's do a little bit of a history of the problem. I think the very first paper which actually gave some result on the topic was a paper from Pizier from 2014, where he basically showed that if you took the dimension of your coefficient to be the fourth root of n, then somehow you could bound the norm of your random matrix by what you expect to be true. I will not be getting into details here, but basically you would get a good answer for this kind of dimension. So to do so, he basically took Hagoop and Peterson-Thom's paper and followed through their estimate and found this bound. Keep in mind though that this was more of a corollary in one of his paper, in his paper. That was not the main result. And then, well, we moved forward by a few years, and so there's this paper of me and then my advisors at the time, Collins and Guillonnet, where we improved that bound to n exponent 1/3. And what's interesting is that that was my very first paper and the beginning of my PhD, and from the story I was told later on, I ended up working on this question because there was a workshop at IPAM in 2018 where I believe Ben met with Benoit and Alice and actually asked them that very question. So it has kind of come full circle, basically. All right, so in this paper, we did the case of G-random matrices. And then the next year, I did the same kind of dimension, but for the unitary case. Then we get this this paper by Bandera, Boidarjo, and Van Handel, in which amongst the numerous theorem and corollary they got, one of them was that you could actually take the dimension to be almost n. So you could almost prove Ben Hayes' conjecture, but you were off by a factor of logarithm of n. And we got stuck on this kind of bound for a rather long amount of time. In the end, it took a few years to actually break the m equal n barrier. And it turns out that, so this was done by Belinsky and Kapitein in 2022. The case is precisely m equal n, where they also assume that your coefficients were actually not deterministic, but themselves random matrices independent from your other random matrices. But anyway, the next year we finally got that actually you could break the this barrier of m equal n and consider coefficient of sub-exponential size. This was done by Bordenave and Collins, and they proved the following estimate. So all right, then we move on by another year, and in July we've got this paper from Chen, Garza Vargas, Trop, and Van Handel, which showed that, all right, so we could, they only tackled the case where m was a little off n, but it turned out that that was the first of a series of papers where they would get to show stronger and stronger estimates. Typically in September 2024, what Maggie and de la Salle did with those results is that they showed that you could go all the way to exponential of square root of n. And then 1 month later, I got this paper where I showed that you could replace square root of n by n exponent to third. And literally 6 weeks later, Chen, Garza Vargas, and Van Handel came back with this bound m equal exponential of n. So this paper, as well as this paper, and I guess this one too, realize they share pretty similar method overall. This one is completely different, and so is this one. And so is this one, actually. So in total, we've got 4 entirely different way of showing, proving the Peterson-Thom conjecture out of Ben Hayes result. All right. So today I'll be focusing on this paper and explain a bit what's the strategy behind the result and give you a few insights. Okay. So let's come back to our original problem. But simplify it even further. If we just take a random matrix A of size n, well, how do we control the norm? How do we capture its behavior? Well, there are basically only 2 ways of doing so. The first one is to study smooth function, and the second one is to do the moment method. And literally every single proof of strong convergence for random matrices relies on one of those 2 things. And in the result I'll be telling you about, I took the moment method approach. So this moment method can be summarized with a few very simple inequalities. Basically, you want to upper bound the expectation of the norm. So what do? You first choose Hölder inequality to take the 2kth root of the expectation of the norm of A exponent 2k. Then you use this operator algebra equality, which tells you that this norm of A exponent 2k is just the norm of A star A exponent k. All right, so far so good. And then, since A star A is a self-adjoint and positive matrix, you can just bound its norm by the trace, the non-normalized trace. And finally, what I want to do is have a normalized trace. So I just divide by n inside the expectation and then multiply by n exponent 1 over 2k. All right, so far so good. But the point is that we've got this thing here, this n exponent 1 over 2k, which a priori is quite bad because n is going to infinity. But if you can take a to be much larger than the logarithm of n, or just a bit larger, then that thing is basically just 1. And so really, the moment of your random matrices stop capturing the behavior of the largest eigenvalue. And so what I mean is that if you can show that for a k sufficiently large, you've got this kind of inequality, then what you will show is that the lim sup, that should not be a lim, that should be a lim sup, of this expectation is actually bounded by this very constant. So the whole point of the moment method is that you want to show this sort of inequality on the moments for k sufficiently large and for c sufficiently small. And of course you're telling me, okay, so here I only proved that the lim sup was bounded by this constant c. What about the lim-half? Well, proving the lim-half is larger than c is usually it's a very straightforward consequence from weak convergence estimate. This is much simpler to do, so you don't need to worry about it. And finally, if you want to study the expectation of if you want to study the norm itself and not its expectation, then you can once again also just use some concentration properties estimates. That's very classical in random matrix theory and not something you should be worried about. At least when working with Gaussian unitary things, models that are very smooth. Okay. So now that I've talked a bit about the moment method, I should talk about the moment method applied to our model. But before I even go back to the case of matrix-valued polynomials, I should take about the basic case where you take P, just a polynomial with scalar coefficients. And the first result of that kind was proved by Voiculescu in the early 90s, where he basically showed that like if you take the renormalized, like the normalized trace of a polynomial, then this thing actually converges towards a deterministic limit. The deterministic limit in question being the trace of like the same polynomial evaluated not in random matrices, but in free semicircular variables. So of course that's not good enough to use the moment method because you're gonna you're going to need to like understand the next order error term, but that's still like very, very important information because that tells us all about what you would expect the norm to converge towards to. Basically, if you know that the trace is converging towards, if you know the trace of your random matrices is converged toward the trace of some operator, then the next question you can wonder is, does the norm also converge? And well, that's something that was done by Hagorb and Anderson in 2002. And the way he did it was this smooth function method. And here, what I'm going to tell you about is about the moment method. And to do so, you really need to understand like every term of the expansion. So what I ended up doing a few years ago is proving that actually, if you take this same model here, this very same trace of a polynomial, but maybe let's say you exponentiate it k times, because that's what you will need to do when doing the moment method, then actually you've got this kind of asymptotic expansion. And in fact, like the fact that you have an asymptotic expansion is trivial. Like this is just, well, all of that is just a sum of like expectation of product of Gaussian random variable. You can just do weak calculus and like you will immediately get some expansion. But what is absolutely non-trivial is how to control the coefficient of your expansion by what you actually want. And so the way, and like why this paper was like so useful for this was the fact that we got some sort of like fully explicit combinatorial expression of the coefficient alpha ak of p, such that you had an immediate like upper bound of this form. And so, right, so now that we have this thing, well, let's try to do like the moment method. So we take k to be like sufficiently small, but much larger than the logarithm of n. And we take this thing here, okay, so we've got some expansion, so we just switch that by the expansion, and then finally we upper bound every single term of the expansion by this upper bound. So we end up with this sum here. So we can then just take out this, this norm of p of x exponent k, just take it out of the sum. And then by summing over I whatever remains, we end up with this exponential here. But here, as I said, we assume that we took k to be smaller than the square root of n. So what this implies is that really the term in the exponential is just 0. Like it's a little O of 1. And so as a consequence, this exponential itself is just 1 plus a little O of 1. And so what you have done by doing so is showing that like the moment of this p of xn are actually very well controlled by the norm of p of x exponent k. And so basically you can just use the moment method with the constant c being equal to this norm of p of x. And that allows you to conclude that you do have like strong convergence for the norm of for like polynomial with like scalar coefficients. And in fact, it also allows you to study a bit the fluctuation, show that like the fluctuation are at most like 1 over square root of n, which is actually optimal when you start considering deterministic matrices, which you can also do, even though I didn't put it in this slide. It's something due to the BBP transition. All right, but before I actually tell you how to move on from the scalar case to the matrix valued case, let me actually give you some insights on that paper. And I would say that like the very basic heuristics in that paper, which is admittedly like a heuristic that was started like already like in my very first paper with like with Benoit and Alice, is that to take some classical idea from like classical stochastic calculus and like transpose them to the free case. So all right, so what are those ideas? Well, let's say that you're given a Markov process with an infinitesimal generator L. All right. So, well, in the domain of, if you take f in the domain of L, then you know that differentiating this thing will be equal to the following quantity. And you also know that like if x infinity is the invariant law of this Markov process, then xt is going to converge in law towards x infinity. You might need some assumption and all of that. I did not, probably you need a few more, this is a very vague heuristic thing. Like, It could very well be that in all generality, it's a little bit more complicated than that. But for the process I studied, like all of that holds. So all right, so since xt is converging in the law towards x infinity, if you want to compare the expectation of f x infinity with the one of f at time 0 of x0, then this is just the integral of the differential of expectation of f of xt. And in turn, that's just the thing right here. Like this is all a very straightforward inequality once you write it down. And besides, you also know that like if x0 has like the same law as the invariant process, then what it means is that this quantity is constant, and so by differentiating it, you just get 0. So what it means is that you want to compare like two variables, like the invariant law of your Markov process and some other variable x0. Then what you should do is just take your Markov process, you start it in x0, and then you just let it go to infinity, and you will get that those expectations satisfies this formula. And then you can try to study that, like maybe for some x0, actually this thing will be small, and then you will have shown that the difference between those two things is small. So that's a way of like understanding how close the law of x0 and x infinity are. And typically, it's like this is usually referred to as like the Stein's method in the Gaussian case, which is like a very, very old method from like the 70s maybe, or maybe even earlier. It's quite old. But anyway, the point is that I kind of want to reuse those ideas, but in the free case. And it's quite nice, because in the free case, there is a wall theory which is equivalent to the classical stochastic calculus, but which, instead of using a classical Brownian motion, uses a free Brownian motion. And this thing was introduced by Bian and Speicher in 1998. They have like, this is when they have their first paper. So all right, so this is what I've called the interpolation method, basically. And the idea is the following. You're given a random matrix and an operator U, and you somehow want to interpolate between the two of them. So what do? You assume that you have some sort of free Markov process whose invariant distribution is going to be precisely U. It might be a bit weird if you only use to like classical probability, but I swear you that there is a way of making sense of all of what I just told you. And so then what you do is you take your Markov process and you start it in your random matrix UN, all right? You can do the same, but instead of like starting it in UN, you start it in your invariant distribution, all right? But just keep that in mind for later. And the point is that, once again, if you take UTN, this thing is interpolating between UN and U. So when you take this thing, which is basically the trace of Q evaluated in your Markov process at time 0, and then this thing, which is the trace of Q evaluated in your Markov process at infinity. Once again, you can just interpolate and write that as an integral, where you've got some expectation of a trace of your infinitesimal generator L applied to your polynomial Q, and then evaluated in like this Markov process UTN. And the thing is, if you remember from a previous slide, I said that like if you start from the invariant distribution, then the term of the integral is just going to be 0. And here we don't start from the invariant distribution, but we start from a random matrix, which is somehow converging in distributions towards your operator for some sense. And so basically that means that the distribution of UN is already close from U. And so that basically this thing here should be close from that one, which is just 0. And so the whole heuristic of this thing is that by doing this interpolation strategy, you write the difference between those two traces as an integral whose term under the integral is like you expect it to be small. And what it turns out is that not only is that actually small, but it's also like you can fully compute it. And so by just bootstrapping, what I mean by bootstrapping is just reapplying the same equality over and over again, you get a full expansion. So all right, so that was the strategy of like getting this expansion, but all of that is like, I would say that was a paper the paper itself dates back from 2020. And it took me an extra 4 years to actually get to the case of matrix-valued polynomials. So that was like something fairly non-trivial that I needed to actually move on to the matrix case.
So for your method without matrix value, so Is there a hope to push it up to the critical scale, like n to 2/3, where you start seeing edge forces, or is it hopeless somehow?
It turns out that like yes and no, in the sense that like I would say that there is a method, but we get stuck on the same thing as like people doing local get stuck on, which is that studying the the spectrum of the stability operator, if that rings a bell. And we need like more or less the same research that like people doing local law needs, and it's the thing is like horrible because if you want to prove it for a given polynomials, then maybe you can really like you do like a bunch of computation, and maybe you will get down to it after like 2 months of computation. But then this will only hold for your given polynomial. There is no way of generalizing that to like any polynomials, at least none that I know of.
But for a given, you're kind of optimistic. So if I give you some polynomial, then you think that you can do it.
Yeah, I would say so, but I mean, not something of degree 150. But you know, like assuming you can compute some Grobner basis, I guess I would say so. Yes. All right. So now let's come back to the case of operator-valued polynomials. So once again, I just put back the definition. This time we've got P of xn, and we've got some sum over monomials of AL tensor L of xn. And what I said was that if your AL are scalar, then you can compute an expansion. If they are matrix valued, well, how do we compute an expansion? Well, there is always the naive solution, which consists in just saying that like if you take the kth moment of your polynomial, well, this is just a sum over all of your monomial L1, L2, and so on, of like the product of the AL1, AL2, and so on. And then here you've got a tensor, and you've got this other product of monomial, Ln1 and L2, and so on, that you then evaluate in your random matrix. And then when you take the expectation of this thing, well, you get something pretty nice in some sense, where like you've got some trace of this, and here you've got an expansion with you've got an expectation of your trace. And so once again, you can just use the previous theorem and say that like you've got an expansion for this expectation, and just plug in like very naively the expansion. And it turns out that when you do so, well, you do get some expansion, and actually like the coefficient beta ik of P are like, they're not that bad. There is a way of like working around with it, and as long as like the dimension of your matrix coefficient is like strictly smaller than the one of your random matrices, then there is a bit of like a 2 pages lemma trick which allows you to still work with it. But what we're really interested by is like the case m equal n, or really like exponential of n, like much larger than n. And then it gets tricky. Because in order to build those coefficient beta ik, what you really need is to use this sort of multiplication map. So where basically you take 2 elements in A tensor B, and on the left-hand side, that's just the regular multiplication, A1, A2, like the multiplication is just A1 times A2. But on the right-hand side, like B1 times B2 has to be B2, B1. So you somehow swap them. So like for people doing operator algebra, this thing is just, it's the multiplication in A tensor B up. And that is tricky. Like this can actually completely ruin your estimate for a pretty simple reason. This map here, like this is not a bounded map for the minimal tensor norm if you take this thing to be the minimal tensor norm. And in practice, like in our case, we always want to work with the minimal tensor norm. So of course, like if you work with like matrix space, so every linear map is bounded, so this is bounded. But it's just that like the constant is very bad, like the norm of AB is smaller than the norm of A and norm of B. Well, if you take this multiplication map, suddenly it will not be nicely bounded by a constant 1. And actually, you can even like take like an explicit example. So this thing here is like rather useful in operator algebra when you're trying to understand how badly behaved your partial transform is. And so really, you take this U here, this sum over ij of Eij tensor Ej, and it turns out that even though this thing is like you're summing like n square different matrices, well, this thing is a unitary operator. And since it's a unitary operator, that means that this thing is just of norm 1. So to see that it's a unitary operator, well, it's rather, well, you just take U star U and you compute it. So all right. you've got this sum over a, b, I, j of e, I, j, e, a, b. And so for that thing to be non-zero, necessarily you need like j equal a, and here you will need I equal b. So out of the four indices, you can drop two of them, and you're left with this thing, which is precisely the identity in Mn of C tensor Mn of C. But then if you look at like M of u, so you're multiplying u by u in this weird A tensor B ob product, well, this time we've got to like switch around those two. And suddenly, we do not have to impose that I equal B. We only have that A equal G, which we already have there. So what it means is that in the sum, we cannot get rid of like like two indices, but only of one. And so what happens is that, sure, when we're summing over I bed and we get I and B, we get U, but then we are left with this extra index going from 1 to n that we're summing on. And so in the end, we get n times U. So what this means is that if you're looking at like the norm of M of UU, normalized by the norm of the vector UU, which is, well, those matrices are just unitary, so that's just one, then you get this n. So that's really bad, because really, when doing your asymptotic expansion, and you're trying to go from like beta I to beta I plus 1, then you will need to use that map M twice, which means that if you do things naively, you will lose a factor n squared. But then when going from like beta I to beta I plus 1, you just go from like 1 over n to I to 1 over n to I plus 2. So on one side, you're like gaining a factor n squared, but on the other side, you're losing a factor n squared, and those two will compensate, which is really bad. So we need to work around that. We need a way to like somehow handle that map, even though it has all of those like really bad properties. So okay, so to do so, we can also try some sort of naive approach. But spoiler alert, it will not work. But anyway, I should still mention it. So this time we're going to like take the map M and like take a slightly more general definition, where like instead of just taking two elements, of multiplying just two elements, we're going to take n of them. On the left side of the tensor, we're just multiplying in one regular order, A1, A2, and so on. And on the right-hand side, on the contrary, we're like just permuting all of those BIs. All right? So that thing is, of course, not great. But like, for example, if B is commutative, then that wouldn't mean much, because you could just permute them all back together in regular order, and you would get that the minimal tensor norm of this thing is just bounded by like the product of the minimal tensor norm of each of those x, j. But then, as soon as like B is not commutative anymore, then really the only naive estimate that you can realistically do is bound this thing by not the minimal tensor norm, but the projective tensor norm. If you don't know what the projective tensor norm is, well, it's okay, you can still follow. All you should know is that basically the minimal tensor norm is like the smallest norm you can have, whereas the projective tensor norm is like the biggest norm you can have. So already you know that like when comparing those two, something wrong is going to happen. And in practice, if you try to compare like the projective tensor norm of like pk of x, you want to compare that with the minimal tensor norm of pk of x, then you would be losing a factor, like a constant exponent k. There is still a way like to do so, but like this is going to be really, really bad. And typically, if you're trying to do some asymptotic expansion, then and to use those estimates, well, what would be like the order n square b? Well, you would have like this 1 over n squared, and then you would lose this constant c exponent k. But as I said, we want to take k to be much larger than log n. So that thing would be really big. Like that would be really bad as an expansion. So that's something that we cannot use. So all right, so what do we do? Like, how do we find a workaround this thing? Well, it turns out that we don't have to just take any b. Like the only like the algebra, the sister algebra b that we're considering is the one associated with a free semicircular system, which satisfies a lot of very nice properties. Notably, there is this notion of like higher inequality, which tells you that like actually the operator norm and like the L2 norm are like kind of related, and that's basically what I built upon. So okay, if you take a family of semicircular variable and you want to take the trace of their product, then there is this result of free probability, which tells you that you can use like the moment QNN formula, and it turns out that the QNN has this very nice expression as like defined with the help of non-crossing per partition, and you get this thing. So okay, forget about that. You got a sum over all possible non-crossing per partition. And what is a non-crossing per partition? Well, I like to visualize it like this. You take a circle, and you put your x1, x2, x3, and so on, like on some notches. And then what you want to do to have like a non-crossing per partition is just link the element here, like all of your notches together. You want to do it by pair. And of course, you want to do it without having any crossing. Otherwise there would not be a non-crossing per partition. So okay, so for example, that's an example. You know, that would be an example of like non-crossing per partition. And you can do that for like for any non-crossing per partition, and just in the end you have to sum them and you will get the trace. All right. But the point is that you can actually use that to somehow get a nice formula for this kind of thing. So here, as you can see, I actually I didn't take the regular product, you know, of A1, A2, A3, A4. I took A2, A1, A4, A3. So I somehow used my the fact, like, I want to tell you that, like, even though like this product is not in the regular order, you can still find a way around this. So okay, so once again, let's take a circle, and then take, on this circle, we're going to put our polynomials. So we've got A2, A1, A4, and then A3. And then I'm going to consider like all of the non-crossing per partition that somehow satisfies what I call a configuration. And what is this configuration? Well, if I take those polynomials, 2, 3, 1, 4, I'm going to say that like 1 is just left alone, 2 is linked with 4, 4 is linked with 3, and 3 with 2. All right. And then I'm going to like consider every non-crossing per partition that somehow are compatible with that configuration. And what I mean by compatible is that in that non-crossing per partition, there will be an element of A2 linked with one of A4. There will be an element of A4 linked with one of A3, and one of A3 with one of A2. But every element of A1, with none of them will be linked with any of the others. So all right, so you know, if I take such a non-crossing per partition, well, I've got some element of A2 linked with A4 and so on. So I've got some of them. But the point is, like, since this is non-crossing, there is a last element in A2 linked with A4. And every other element here will not be able to be linked with A4, because then it would somehow contradict the non-crossing property of like our non-crossing per partition. So I will denote this element with a special notch. And then we can just also, you know, keep on doing the same. Well, like, we've got some element of like A2 linked with A3 and so on, and we just keep on going. And at some point, there will be a last one, you know, like a last element of A3 linked with A2 that we will also denote with like some sort of like red notches, not red notch. And then so on, like same thing for like A3 and A4. All right, red notch. Okay, and then what I do is that like I divide those polynomials here, like this polynomial A2, I divide it into parts, like between here and here. So that would be A21, A22, or maybe the other way around. I'm not sure how I went here, but whatever. Which one was it?
A21 seems to be linked with A4 too.
All right, then it's all right. And then A31, A32, A41, A42. Okay, no, that's, well, whatever. The point is that once you have done so, you're going to consider every single non-crossing per partition that not only satisfies that configuration, but such that the last element linked with like some other polynomial is like one of those red notch. This is very important. And then if you consider the set of all of those non-crossing preparation, then somehow this set of non-crossing preparation will factorize in a product of sets. And each of those sets are going to be the following. You will have the set of all partition of non-crossing preparation on A1, the set of non-crossing preparation on A21 times A42, the set of non-crossing preparation on A32 times A41, and then this set of non-crossing preparation. And so what this means is that, once again, you can use the fact that we've got this, expression for like the trace of a product of a free semicircular variable to deduce that actually those things will give you terms of that form. Some trace of A21, A42, some trace of A3, trace that should be trace of A1 because visibly I took different convention here. But the point is that you will get a product of such traces. But here, as you can see, in each of those traces, either we've got a single polynomial or we've got like two of them, like two subsets of them. But here, by traciality, you can somehow swap them. So their order does not matter. And once again, like a product of traces, well, it's a product of scalars, so you can swap them however you want. And so basically, even though here you've got this order like A2, A1, A4, A3, well, here it's all commutative. You can just like swap them back together. And you can even use like this kind of like trick to basically have like a perfectly normal order where you get like small a1, small a2, small a3, small a4, instead of having this like mixed order. We've got like 2, 1, 4, 3. And so of course, like this is just one term, like you will get many of them, but it doesn't really matter because the point is that all of those terms will be a product of like traces and correlations. And so I guess that I get this horrible formula that you should not look at, not during that talk at least. Here, I would advise you to just listen to what I'm telling you. But the point is that if you take a product of like monomial, then this is actually, there is a way of expressing it as with a formula which only depends on the trace of each of those monomial and on their correlation. But by, once again, the correlation by traciality, you can just switch them. And so the point is that in some way, the formula here, it doesn't depend if you're permuting the AI. Like if you're permuting them, well, it will still be like more or less the same on the right-hand side because it only depends on the correlations and the traces. And that's really like, for me, it's really an equivalent of high-group inequality because high-group inequality was telling you that if you look at like the pth moment, you could control that with just the variance. And here that's the same. If you take like a mixed moment of product of AI, you can control that with like the traces and the correlations. So that's really an equivalent. Yeah?
Could you say a little bit about what the delta is?
So, all right, so delta is like, it's basically a projection. The point is that usually you want to kind of keep track of like how many...
Okay, so this is just to sort of artificially enforce this connection that you're witnessing in the diagram.
Exactly. Like, I guess if your x have no, like they all have the same correlation, it's literally just the projection in the Fock space minus the one on the empty vector. Mm-hmm. Okay. And so the point is that I've just spent like the last 5-10 minutes to like telling you that thanks to this equality, you can basically ignore like the mixing of your monomials. You can, if I were to go back to this thing, well, basically the fact that here we're multiplying with the help of this weird permutation doesn't matter. We could just take the permutation to be the identity. Okay. Well, of course, this comes at a cost because doing so means that you need to somehow isolate those red notch here. And isolating those red notches really just means that you're like differentiating your monomials, basically. And so by doing so, that means that like you have to go from like bi to bi plus 1, so beta I to beta I plus 1. Instead of differentiating 4 times, you will need to differentiate a lot more. So you will need to differentiate 16 times, which may appear like a lot and is. But anyway, in the end, you get those kind of things. And sure, it's a lot, but it's polynomial in K. And polynomial in K is fine. Like what I really didn't want was like the the exponential of k. That is really bad. So once you've done this, you can come back, to the moment method. So this time, your P of xn is a matrix of size mn by mn. So when doing the moment method, instead of having n exponent 1 over k, you will have nm exponent 1 over k. All right. Then you've got the expectation of the trace of p exponent k, which you can just replace by this asymptotic expansion, and then you can use the bound that we just showed here. You just plug that in all the and since we assume that like k is a little of n exponent 1 over 8, then that implies that like this is the sum over I of like something small exponent I. So that's just a constant. And then you take like the kth root of that constant. That's just 1. And so you're left with like m exponent 1 over k. And by being left with m exponent 1 over k, since we can take k to be all the way to like little of n exponent 1/8, that means that we can afford to take m to be of the form exponential of n exponent 1/8, and that thing, this m exponent 1 over k, would still be small. You would still get 1. And that's how you would get some estimates. The issue, as you can see, is that like here we have like this n exponent 1/8, which is not as good as the n to third I like first announced at the beginning of the talk. So one should understand, like where does this thing come from? Well, it's mainly because, as I said, this thing here, you have to differentiate 16 times. But most of those differentials, like, they are fake. They should not be there in the first place. And so how it translates is by the fact that you actually gain this sort of like 13i factorial, which might not seem, like something very interesting because k is much larger. K is like, depends on n, whereas like 13i does not. But the point is that there is a bit of a computation trick where basically, now that you've got this term, what you can do is you take the 13th root of that thing, all right? And then by summing over g, by replacing 13i by g, well, what you will get is that you get this exponential of like k exponent 16 over n squared, but then you take the 13th root of that. But then eventually you're still taking the kth root, and the kth root, like, it doesn't matter whether you're taking the 13th root or not inside. And so in the end, you can get rid of a lot more k, and what you will get is a ratio of k cubed over n squared. So that was a little bit fast, but this is a trick that I thought was interesting to mention, even if it's a little bit unpractical to explain aloud. But the point is that you can recover this ratio of k cubed over n squared, even though we have to differentiate a lot more times. And then, well, once you've got this ratio of k cubed over n squared, that means that you can take k to be of order little o of n to third, and that will still be small. And then you can take m of this form, exponential of n to third. And so finally, we get the following, basically. We get that we have, like, if we have some faithful threshold sister algebra, and then we've got some polynomials, some random matrices, some free semicircular variable, then we can control the L to K norm of this random operator by the deterministic equivalent, like the free equivalent, times something which will be small. And of course, in all of that talk, I've only ever talked about matrix valued polynomials, but you can do so with like any operator valued coefficient, like polynomial. Like as long as A has to satisfy some assumptions, like this would work, but I'm pretty sure you could like have like much weaker assumption. And of course, like if you take that inequality and you take M of that form, then you will get that really this expectation is controlled by the free limit. One thing I should also mention is that if you want to add in some like deterministic matrices on either side of the tensor, and like whether it be on in the coefficient, well, of course that we can do, but also on like the random side, there is a way around it, although it's not quite satisfying. Like if you want m equal n and have deterministic matrices on both sides, you're going to have like some issue. But there's a way around it. Okay, so that's more or less where I wanted to get to. But before I actually conclude that talk, I should mention a few other results. So first, there is this thing with, I did the whole moment method, but it turns out if you want to like still study smooth function, since I have like those huge formula for asymptotic expansion, you can just take your function f, use Fourier inverse theorem to say that you only need to study the exponential of your matrix, and then the exponential of your matrix you can just like brutally approximate it by like its power series, and then you can use the formula, the explicit formula, to deduce some like an expansion for like this kind of expectation of a trace of two smooth functions. The one thing to keep in mind though is that in order to do so, f has to be like very smooth in the sense that like for every power of n squared that you want to gain, you need to be able to differentiate your function f an extra 16 times, which is a lot, and also like should not be there. Like I think 4 times is what you would expect for most models. And also like what you would get if you didn't have those matrix coefficients. All right, and then as a last thing that I should mention is the fact that if we take this operator, which is the one that I was talking about a few slides ago, and that this time instead of taking B any system algebra, we take the system algebra generated by 3 semicircular variables, then actually it is not, if we want to like study the minimal tensor norm of that thing, we don't just have to bound it by the projective tensor norm of the PNs. Somehow if those things are polynomials, there is something called like that we call like the F norm, and this F norm is a lot more well behaved than the projective tensor norm. So of course that comes at a cost, where you've got this constant C and D, but that thing is like, it grows like polynomially with like the degree of your polynomials. It's not, it doesn't grow exponentially, which is what we really want to get. And a typical example is that if you take like, the moment of a polynomial of x, so p of x exponent k, well, the f norm of that thing will be controlled by the minimal tensor norm exponent k up to k exponent 3n. So really, that is like much, much nicer than the equivalent, where if you take the projective tensor norm, and here we would have the same thing, but here you would have a c exponent k, which would not be interesting. But yeah, as a conclusion, it's like the really like the key that I needed to like move on from my paper from 2020 to like this result with like matrix valued polynomials was some sort of like fast decay property satisfied by the system algebra of a free semicircular system. So thank you for your attention, and that's it.